Hi, and welcome to this first recitation problem video. So the first problem I'm going to do is this one. We're given a complex number and we have to convert that from rectangular form into polar form. So the complex number here is 4 plus 2j. So this is in rectangular form, and what we have to do here is we have to take this number and convert it into polar form. So if you want to do that on your own, and pause the video, and I guess I'm just going to assume that you've unpaused the video, so I'm going to start going through this now. So pretty much what you're doing when you're putting this into polar form, if this is rectangular form, the form of polar form is going to be whatever your magnitude is times e to the j, whatever your phase angle is. And actually, instead of phi, I'm going to write theta up there. So pretty much what you use to convert this is Euler's identity. Is what you're going to use to convert this from rectangular form into polar form. So pretty much what we're going to be using for the first whole bunch of videos for this recitation especially is Euler's identity, which is that if I have, let's even take the m off of there for a second. If I have this number, e to the j theta, that this is equal to the cosine of that theta plus j times the sine of that theta. So this is Euler's identity. And this is the, I guess, the big equation, the big theorem, I guess, that we're going to be using for a while in this recitation, really for a while in all of signals. The only additional thing I'm going to put onto this to kind of modify what we have here is if I multiply both sides of this equation by what I'm going to call my magnitude, which I'm just going to say m. So if I multiply m e to the j theta, then I just multiply each of these two terms as well by m. So I have m cosine theta and m j sine theta. So now I've got pretty much a magnitude factored in here. And pretty much what you can see here, and maybe you might remember this a little bit from trigonometry or a little bit from physics, is that if I have, let me just go ahead and draw some axes. So that's my y-axis, this is my x-axis. And let's say I had a point out here, and I drew a line up to that point. Let's say I wanted to know, let's say I knew how long this line was. Let's say I'm going to call that line L. I'm going to call that line L for length. And let's say I also knew what the angle was here. So I knew that angle was theta. If I know those two things about where this point is, I know what angle it is from the x-axis, and let me label my axes too. This is my x-axis, this is my y-axis. If I knew what angle that line made with the x-axis in this fashion, and I also knew the radius, like how far away that point was from my origin, how would I find out what its y-coordinate and x-coordinate were? And hopefully you can see that I can use trigonometry to do that. If you were in physics class, you would be doing the exact same thing, or if you were in trig class, you would be doing the exact same thing to figure out what my x-coordinate and y-coordinate were for this point right here. So my x-coordinate is just going to be my length L times the cosine of that angle. That's going to give me my x-coordinate. My y-coordinate up here, let me even choose a different color up here. So my y-coordinate up here, I would just, instead of using the cosine, I would just use the sine up here. So I would still multiply by my radius, how far I am away. I still multiply by that length, times the sine of that angle theta. That would give me my y. So now you can see I've got two terms here. One has cosine, one has sine. That's very similar to what we had up here with this Euler's identity equation that we have. And even what we can do here, if we want to have a real simple way of translating something that is pretty much some number, like everything over here, if I had cosine theta and say theta wasn't changing, then m times cosine theta, that's just going to be a constant, right? If I just call that a. And similarly, over here, if I have m times the sine of some other, well, it's not some other, it's the same angle, m times the sine of that angle, that's also a constant, right? So I'll just call that over here b. So I would have this in the form of a plus j times b. So now that's rectangular form, right? That's the exact same form of our original problem that we were given. So what we can do here, and pretty much what we're going to be doing for a long time in this course, is we can draw our axes again, and instead of saying x and y, I'm going to call what used to be my x-axis, I'm going to call that my real axis, and then I'm going to call what used to be my y-axis my imaginary axis. Hopefully this isn't too new for you. If you've been watching the lecture videos, hopefully this is just reinforcing the lecture, so I'm hopefully not giving you anything that's too new here. But if I have a real axis and imaginary axis, if I were to do this same exact problem over again, and let's actually not do this arbitrary case, let's actually do the exact case that we had right here. Let's say I had 4 real units, right? Because this is my real part, that 4 is my real part, and that 2 is my imaginary part right here. So let's say I had 4 real units, so I'll just count over 1, 2, 3, 4. So this is my real component of this complex number that we have. And then I've got 2 imaginary units, plus 2 imaginary units. So I go positive 2 in my imaginary direction. So now if I were to plot that complex number on my real imaginary axis, it would come out to be right there, because I've gone over 4 units in the real direction and gone up 2 units in the imaginary direction. So that is pretty much where my complex number would fall on my real imaginary axes. So now let's go ahead and do the same exact thing that we had up here, but now we're going to do it down here on this real and imaginary axis. So now I pretty much know that this length right here, this distance right here is 4. I know that this distance right here is 2. And now what I want to figure out is how far away is that point from the origin. And I'm going to call that m. And at what angle? Theta. And if I can figure that out, if I can figure out what this m is, that magnitude, m is for magnitude, and if I can figure out what the phase angle is, what my theta is, that's exactly going to be what my m is here and my theta is here. And hopefully you can see how this works out to be similar to the example we did earlier, where I have L cosine theta is equal to x. Well, that L cosine theta is equal to x, that was just that distance right here was my L cosine theta. And then my y distance up here, that was my L sine theta that I had. So therefore, if I can figure that out, I'm pretty much done. I pretty much have the form that I need or I have what I need to put this into polar form. So now, how do I figure that magnitude out? Well, this is a right triangle, right? If I were to take this exact same line right here, I'm going to redraw this line, but I'm just going to draw it a bit bigger. Let's say that that's my m. I already know that I go over 4 units, that is 4 units this direction, and then I go up 2 units that direction, and I also know that this is a right angle, I can just use the Pythagorean theorem to figure out what that magnitude is, right? So I know that 4 squared plus 2 squared has got to be equal to m squared, or I can just take the square root of both sides, and I know that m has got to be equal to the square root of 4 squared plus 2 squared. So 4 squared is 16 plus 2 squared is 4. So the square root of 16 plus 4. So my magnitude is going to be equal to the square root of 20. And I'm just going to simplify that a little bit. So I know that 20 is equal to 4 times 5. So if I were to take this, that would be the same thing as the square root of 4 times the square root of 5. So I can simplify that down to be 2 root 5. So that's my final answer for my magnitude. My magnitude, I know, is equal to 2 root 5. And now let's figure out what the phase angle is. So my phase angle would be here. That's my theta. And in order to figure that out, I can use I could use a bunch of different things. I could use an arc cosine. So cosine, sine is opposite over hypotenuse. So cosine would be adjacent over hypotenuse. Because I now know what the hypotenuse is, I could use that. I'm going to use my inverse tangent to figure this out. So if I were to take the tangent of my opposite side, so opposite over my adjacent side is right here, my opposite is the 2, my adjacent side is the 4, that would give me my theta. That would give me my phase angle that I'm looking for here. So let me just go ahead and figure that out. So that would obviously be the inverse tangent of 2 divided by 4, so that would be the inverse tangent of a half, would be equal to theta. And at this point, I'm going to get my calculator. And do I have, I don't know if I even, oh good, I do have inverse tangent. So now I'm going to do 0.5, oh, and I'm in degree mode, so I have to set this to radian mode. That's a good point to make. Always make sure that you've got your calculator set in radian mode for everything you do in this course, particularly. Everything you do in this course is in radians. So I do 0.5 shift inverse tangent, and I get that phase angle is 0.4636. So that phase angle is 0.4636 radians. So now I can write down my final answer. I've got my magnitude, I've got my phase angle, and now I can write down that my final answer for this problem, that 4 plus 2j, I'll write it up here, 4 plus 2j is equal to 2 square root of 5 times e to the j phase, which is 0.4636. And that's it. That's the final answer. That's everything you have to do. So anyway, hopefully you found that useful. And I guess I'm just going to keep doing a bunch more of these recitation problems. So hopefully you found that useful. And hopefully I'll see you in a future video. Thanks for watching.